This is Algebra 2 Lesson 2-7, absolute value functions and graphs. An absolute value function is a function in the form of f of x equals the absolute value of mx plus b plus or minus c, where m cannot be 0. Which means you're basically looking at an equation that looks like this. Y equals the absolute value of x plus 2, or f of x equals 3 absolute value of x minus 4 plus 6. All of those are absolute value functions. Fairly complicated absolute value functions, but not too difficult to deal with. The axis of symmetry is the line that divides the graph into two parts, which are mirror images of each other. So if I had an absolute value graph that looked like this, my y-axis would be my axis of symmetry, because the y-axis right here puts it into two mirror images. If I fold it along the y-axis, half of the graph will land on the other half of the graph. A vertex is the turning point of an absolute value graph. It is either the minimum or maximum point. So this point down here in this graph would be the vertex, and it would be the minimum point. It would be the lowest point of the graph. All right, let's take a look at an absolute value graph for just a moment. The parent function of an absolute value graph is f of x equals the absolute value of x. That's your parent function. If I was to make a table of it, the table would look similar to this. If I let x equal -3, the absolute value of -3 is 3, the absolute value of -2 is 2, the absolute value of -1 is 1, and so on. Therefore, when I graph it, I get an absolute value graph that looks like this. They're very easy to graph. Actually, you only have to graph one half of them. If I was to graph the point -3, 3, here's the point -3, 3, -2, 2, -1, 1. The other points are mirror images. So if this point here is 3 units to the left of the y-axis, I have to go 3 units to the right for its partner, 2 units to the left, 2 units to the right, 1 unit to the right, 1 unit to the left. Okay? The slope is up 1 over 1, up 1 over 1, up 1 over 1, as you can clearly see. Or down here, down, right, down, right, down, right. Okay? So you can see that they're mirror images of each other. Absolute value graphs are not hard to graph. So if I'm going to graph an absolute value function, it's going to follow the same rules pretty much as what we did yesterday. So if we were to look at the absolute value graph of y equals absolute value of x, here's the graph of y equals absolute value of x, 1 over 1 over. Okay, so I'm trying to graph this to the best possibility. Nice straight line that way. Nice straight line that way, so much straight line. That's the value of y equals absolute value of x. Now, if we were to follow the same rules as yesterday, this would go up 4 units. Okay? And if I was to think about it, if my original point was 0, 0, the absolute value of 0 plus 4 moves it up 4, so it's going to follow the exact same rules as yesterday. Or the last lesson, I should say, not necessarily yesterday. So my graph should look like this. There's the graph of the absolute value of y equals the absolute value of x plus 4. And just moved it up 4 units. If I was to graph again, absolute value of y equals absolute value of x. Let's see if I can draw a better line here. Let's see here. There we go, it's much better. Absolute value graph, a little straighter. Now, if I was to do the absolute value of x minus 3, we're going to go down 3 units this time. So in this particular one, let's make this 7, 3, 3, this could actually look like this. This could actually look like this, and I could actually make a straight line, so there we go. So then you get the absolute value of this one is y equals the absolute value of x. This one is y equals the absolute value of x minus 3. So it follows the same rules as the previous lesson did. The translations of the previous lesson also apply to all your absolute value functions. So once you can graph your absolute value functions, it's actually pretty easy to be able to translate them. Okay, so same translations. Instead of where there were parentheses on the last lesson, and now are absolute value symbols. So the same rules apply. That's what I like about math. It's just it goes a little bit further each time, adds a little bit more detail, but doesn't change everything altogether. So we are going to look at all of these things just like we did
the last lesson. So if I'm going to combine a translation here, I have y equals the absolute value of x, and y equals the absolute value of x minus 2 plus 1. Now, I do not care if you draw in the parent function first and then translate it. Some people need to do that in order to be able to draw the translated function. And some people can just go straight to the translated function. I'll do both. The first one I'll draw both of them in, and the second one I will only draw the translated function, so it'll make it easier. All right, so let's do the absolute value of x. So let's see here, I want to do this in green. So here's the function of y equals the absolute value of x. That one. There. Now if I'm going to do this, this is going to go left 2, and this is going to go up 1. So I'm going to take every point, translate it 2 left and 1 up. So I'll start with the origin. I'll go 2 left and 1 up. From here, I don't need to translate any other points. I can just remember my slope is up 1 over 1. And I can just make my v-graph from that. And there's my new translated function. So as you can see, if you can find where your vertex is, it's actually very simple to translate a absolute value function. Whoops, I messed up. And let's go back. I did a common mistake that most people do. This is not left, it should be right. It should be right 2 and up 1. That's a common mistake, and I tend to make it more often than I would like. Pay attention. If it's in the absolute value symbol, it does opposite what your brain thinks it should do. So I should go right 2 and up 1. So my graph should actually look like this. Let's fix that really quickly. Sorry about that. This goes through, but not everything's perfect. And it's a good idea to look at things before you move on, because as soon as I looked at that, I knew it was wrong. So this would be the equation of y equals the absolute value of x minus 2 plus 1. And the green one is y equals the absolute value of x. Okay. So let's take a look at the next one. Letter B here. I'm going to move left 3 and down 1. Okay? Left 3, down 1. Well, I know the vertex is normally at 0, 0, so I'm going to translate that vertex 3 units to the left and 1 unit down. So here's where my vertex is. Now all I have to do is go up 1 over 1, up 1 over 1. Make mirror images on the other side. And here's my graph. And that's the graph of the absolute value of y equals the absolute value of x plus 3 minus 1. You don't have to draw the parent function in every time. If you can do it without drawing the parent function, that's great. If you can't, make sure you label the parent function and then label the transformation as well. All right, we've already talked about this. The right branch of the graph of y equals x, the absolute value of x has a slope of 1. The graph of y equals a times the absolute value of x. A is greater than 0. It's a stretch or compression. Okay, if a is greater than 0, it's a stretch. If a is less than 0, it's a compression. Its right branch has a slope of a, and if you have, notice this is a reflection. Okay, the graph of y equals negative a absolute value of x is a reflection of that in the x-axis, and its right branch has a slope of negative a. We've talked about that. We talked about how the slopes on the right-hand side is a positive 1 over 1, and the left-hand side is a negative 1 over 1. So let's take a look at some graphs. A vertical stretch and compression. Let's compare y equals absolute value of x and y equals negative 2 absolute value of x. And I'm actually going to draw the original one just because it's a little easier to compare. So if I was to draw the original one, make sure this is right, get this right, green. So if I have, here's y equals the absolute value of x. There. Now I'm going to do negative 2 absolute value of x. So I'm doing two things to this. It's reflecting over the y-axis, the x-axis. Okay, this is a reflection. This is going to make it reflect over the x-axis. And it's also going to stretch it. So you do two things. Notice you'll never reflect an absolute value graph over the y-axis because it's going to just land right on top of itself again. Because if you put a, if I was reflected over the y-axis, I would put the negative inside of the absolute value, and that's just going to make it that anyway. So you're never going to reflect over a y-axis for an absolute value graph. You're going to reflect over the x-axis, but not the y-axis. All right, so now all I have to do is instead of using the fact that I have, well, let's just take a look at something. Let's make a table. I'm going to make a small table because I want to show you what works here. Let's say that x is -2, -1, 0, 1, and 2. The absolute value of -2 is 2. Times that by -2, you get -4. The absolute value of -1 is 1. Times that by -2, you get -2. Times 0. And the absolute value of 1 is 1. Multiplied by -2 is -2. And so it's 4. So if I was to put these points on the graph, okay, I have 0, 0, -2, -4 is there. Its counterpart is there. Okay, 1, -2 is here and here. So this is what this graph looks like. Now, I don't like to make tables every time, but I made a table for this one just to sort of check for the points. Notice here, in the green graph, the slope was up 1 over 1, up 1 over 1, up 1 over 1, or down over, down over, down over. It's -1 or +1. Okay. Let's take a look at the slope of this graph. Okay. The left branch is up 2 over 1, up 2 over 1. The right branch is down 2 over 1, down 2 over 1. Okay. Which means this -2 is the slope. So once I have the vertex, all I have to do is apply the slope to draw my branches. Okay. I don't have to make a table anymore. I don't have to do this fancy table anymore if I know what my slope is. Okay, because that helps me figure things out. It helps me to realize, wait a second, that -2 becomes the slope of my graph, and therefore I don't longer have to make a table. So, on the second one, letter B here, I'm going to do my absolute value of x, but my slope now is going to be -2/3. So, y equals the absolute value of x. There's no plus or minus, so our vertex is going to be at 0, 0. So I'm going to plot that point first. Here's 0, 0. Now I'm just going to go down to right 3. So here's that point, down to right 3. Its counterpoint would be here. From here I'm going to go down to right 3. So there. So this one is 1, 2, 3, 4, 5, 6. So I go 6 units to the left, and here is my graph. And notice since it's a fraction, it's a wider graph. Okay. The blue graph here on the left for letter A is a stretch, okay. And the fractional graph, or the graph for the red one, is a compression. Okay. So this is the graph of y equals -2/3 absolute value of x. And so once you can find your vertex, absolute value graphs are actually very, very simple to graph. And these two things here lead to a general form of the equation. You combine the stretches and the compressions with the equation translation to write a general form for the absolute value function. The general form for the absolute value function is y equals a absolute value x minus h and your absolute value plus k. The stretch or compression factor is the absolute value of a. Okay. The vertex is located at hk, and the axis of symmetry is the line x equals h. Okay. So, let's take a look at this. It says, compare y equals -2 absolute value of x plus 2 plus 3 with the parent function without graphing, where the vertex, axis of symmetry, and transformation of the parent function. So, this isn't too bad. My vertex, remember, my vertex, if you look back at the parent function up here, it says the vertex is located at hk. Okay. So, if I have the equation y equals -2 absolute value of x plus 2 plus 3. Okay. This is h and this is k, which means my vertex is equal to -2, 3. Remember, it's the opposite inside the absolute value of what you think it should be. My axis of symmetry then is the line of x equals h, so my axis is x equals -2. Okay. And so this graph is translated 2 units left, 3 units up, and stretched by a factor of -2. Okay. Stretched by a factor of 2 and then plotted across the x-axis. That's a lot of things to say, but we'll do that. And it's translated 2 units left, 3 units up, stretched by a factor of 2, and reflected over the x-axis. Oh, I can spell it that way. Ooh, that's terrible. There we go. You will have to memorize the general form of the equation for absolute function. Very, very important to know. The more you use it, the better chances you have that you will memorize it. All right, so let's compare y equals -2 absolute value of x minus 1 minus 3 and do the same thing. Okay, remember h. Okay, so my vertex is 1, -3. My axis of symmetry is x equals h, so that would be x equals 1. It is right 3 units down, right 1 unit down 3 units. Okay, so translated. Right 1 unit, down 3 units. Okay, stretched by a factor of 2. And reflected across the x-axis. Can we write an absolute value function if we're given a graph? Okay, so here are 2 graphs. We're going to write the absolute value function between these graphs. The first thing you want to do is identify your vertex. That's the easiest thing to do. So if I was to look at this point right here, this is at -1, -2. Okay, so the point is -1, -2. So the vertex is -1, -2. So that means h equals -1 and k equals 2. Okay. The second thing you want to do is identify A, the stretch or compression, by looking at the slope of the line. So let's take a look at the slope of this line. Okay, if I look at this, I notice it's down 1 over 1, down 1 over 1 over 1, so the slope is 1. Okay, so the slope equals -1. So that means A equals -1. Okay. And the third step is to write the equation. Okay, so now that you have all that, we need to write the equation, and if you remember the equation, okay, the equation is y equals a absolute value of x minus h plus k. So let's just plug it in. Y equals, my a is -1, so I have a -1 absolute value of x minus a -1. I'm going to write it in that way for a minute and I'll fix it. Okay? Plus k plus a -2. I'll write it in that way. So now I'll simplify it. I just wrote it in exactly as it looked. Now let's simplify it. Y equals negative absolute value of x plus 1 minus 2. And there's your root. Okay? And you can have the 1 in front of the absolute value, or you can just have a negative sign. I prefer the negative sign only. Some people prefer the -1. It doesn't matter. It doesn't change it. Okay, so that's all you have to do. Look at the vertex, identify your slope. Once you've done that, you've figured out h, k, and a, and you can just slide it into your equation. So let's set one over here. Okay, let's identify my vertex. My vertex is right here, which looks like it's a 2, 1. So h equals 2, k equals 1. Okay, let's identify the stretch. Okay, so I'm going, if I look at this, I'm going up 1, 1, 2, 3, right, 4, looks like up 1, right, 4. 1,
there. So it's up 1, right 4, so my slope is 1/4. So A is 1/4. Knowing that, I can write my equation now. Okay, so y equals A, absolute value of x minus h, is A. That's good. And it plus a 1 because the fact that the positive. So 1/4 absolute value of x minus 2 plus 1. Simple as that. That's absolute value graphs. Absolute value graphs are actually really easy to graph and fairly simple to work with once you understand they are simply mirror images. Each side is a mirror image of each other.